So I think now I can start. So let me share my screen. So, well, first of all, I should, give us some caution or warning that this talk is not going to be about something finished or endeavors that have been published or peer-reviewed or accepted by the community. It is going to be more of the nature of an initiative, a proposal for progress in foundations of physics. And it has three main themes. The first one is to look at the history of physics. The second one is from epistemology to emergence and to a field theory of temperature or entropy. Well, that is controversial, but I will talk about it. And the third one is a kind of rationalist, okay, let's call it transcendental rationalist in the sense of Kant, of trying to make an honest progress in the foundations of quantum mechanics. And if there will be any additional time, there are two other topics that they are minor. So let us have a look at the attempts of unification so far. The classical old attempts that Einstein was the main proponent of that. First, we must recall the lesson of general relativity. And the lesson of general relativity is that all potentials must be replaced by the metric tensor. There must be no potentials in the new language that general relativity proposes to us. So, in that view, if you look at most of the atoms of Einstein, Einstein did, a huge literature there is on atoms of Einstein. He tried torsion, he tried teleparallelism, he tried all kinds of different attempts. But in his autobiography, what is happening here? So do you have my voice? Okay, so everybody. Okay, so everybody, please mute yourselves. I think yes, everybody is muted. So I continue. Well, most of the atoms of Einstein, I told you there are lots of atoms, but the most famous one in his autobiography, which he described it as the most promising one, is to decomposing the metric tensor in two parts, a symmetric part and a skew symmetric part. The symmetric part corresponds to the usual gravity in general relativity, the metric tensor of general relativity. And the skew symmetric part corresponds to the Faraday tensor, the field tensor of electromagnetism. Well, I have a serious objection to this one. Well, there are two objections. Even if you do not pay enough attention to the lesson of general relativity, which is no more potentials. Potentials must be replaced by the metric tensor. Even if you do not pay attention to that, there is another problem. Metric tensor represents potentials. It's the new potential. But the Faraday tensor is a field. So you are here gluing two essentially, basically different things together. And I do not see that as a deep enough attempt for unification. And the second problem, well, yes, that is, we must take the lesson of general relativity of replacing all the potentials, no matter whether they might be vector potential or whatever, we must replace all of them by the metric tensor. So Einstein, in my opinion, was so pleased with the Faraday tensor and with getting Maxwell equations, he thought of a kind of, he imagined of a kind of theory which will give both Maxwell's equations for the Faraday tensor and the field equations, the Ricci in terms of Ricci curvature. I think that is not taking the lesson of general relativity seriously. So that was the atoms of Einstein and his followers, most of the atoms. Well, John Moffat also pursued this attempt, but did not identify this Faraday tensor with the electromagnetic, but that is a minor point. So even he, in my opinion, failed for that. So that was the atoms of Einstein. So the atoms of Kaluza. What are the problems with atoms of Kaluza? Well, Klein is a different story because he's adding quantum and stuff, but I want to talk about Kaluza. In my opinion, there are 4 problems with atoms of Kaluza. The first one is what I already said, that it is not respecting the GR paradigm of change of language, that there must be no potentials anymore. So potentials must be replaced. And the second one is, if you look at the metric of Kaluza, which is a 5-dimensional metric, he is forcing a special form for the metric, and that is not the right way to look at a field theory. Einstein equations must tell you what the field components are, what the metric components are. You must not force them by hand manually. So that is another problem. The third problem is the phi field. Well, people try to connect it to quantum mechanics, but I do not think that is a good approach, because we are talking sheer classical field theory at this level. And well, I have many other attempts, but also they failed in various ways, these phi fields, of trying to interpreting these phi fields. And the fourth problem is the vague extra dimensions. So, Dr. Rovelli, are you hearing me? Oh, okay. So vague extra dimensions. What's the problem with the vague extra dimensions? First of all, I have no problem at all with extra dimensions, as long as you tell me what are those extra dimensions. Well, in string theory, people add, I don't know, some number of additional dimensions, and they say we cannot see them. So I am a kind of idealist here, Kantian idealist, and I say, okay, we are not talking about nature per se, but we are talking about nature as presented to us. And if we think about that way, something that we cannot see, something that we cannot see just doesn't have no meaning for us. But there have been some good attempts in trying to clarify these extra dimensions. And these attempts are the book that shown here. They try to identify the 5th dimension with mass. Well, I was working on these lines of trying to interpreting the 5th dimension as mass. Um, and there is a strong maxim for me that um, mass and electric charge must be treated on completely equal grounds. That is a kind of guiding principle for me. So I said, okay, if the fifth dimension is mass, the sixth one must be electric charge, let's assume. And it occurred to me that we are just taking all the basic units of physics, which are space, time, electric charge, mass, and temperature. We are all taking all these extra dimensions as new dimensions, new fundamental dimensions. And it occurred to me, well, it might be the case that even temperature is a fundamental entity. And then I recalled a very old problem that I had with statistical physics. People never take that seriously, but let me go to that. And that is, physicists are kind of sloppy with their definition of temperature. So they say in all required assumptions of thermal equilibrium, we define temperature to be a emergent property of a large number of particles, or ensemble of particles. So if you look at this definition, you see that dimensions of entropy, which is joules per Kelvin or energy per temperature, you are defining temperature using temperature. So that is a serious problem for me. No, people do not take that seriously, but I think that is a serious problem. And nobody has really give me an honest answer. So I agree that emergence, this kind of description of temperature in terms of entropy is a good one, is a useful one, but I do not think it is a rigorous definition of how temperature arises as an emergent property. So I came to the conclusion that basic units of physics cannot be explained to be emergent. And that is very simple for me, at least, to see. If you think that, okay, what is physics about? We always want to talk quantitatively. So if you want to talk quantitatively, this is the lesson of Euclid. If you want to measure the length of a line, you must first choose a basis with which you compare the lengths. So this base one are our base units of physics. So as long as you want to create quantitative physics, you have to choose some basic units. You can change them and change them to something new, different from what they are now, but there is always some basic units. Okay, I cannot see any other way. If anybody can, I would be pleased to hear that. So you have some basic units, and you build a whole structure of physics based on those base units. And so the question is, okay, you created physics, and now how are you going to ever explain emergence of a basic unit? Any kind of explanation that you are going to give me must be in terms of those basic units, because we are in physics and we want to talk quantitatively. So I think basic units of physics, which I think the best choice of these basic units is space, time, mass, electric charge, and temperature. So first, I took temperature as a fundamental property of particles. So these are two principles. Single particles possess temperature. I know it is controversial, but I am going to elaborate a lot on that. and rest ordered energy of a particle is given by this. Okay. Um, and if you do that, it is very simple step. You just add temperature density per volume to the current density of electromagnetism, and by Maxwell's equations, you will get a field equation for entropy. That is one attempt. And the other attempt, well, the problem with this attempt is that the right-hand side constant seems so enormously tiny. So it seems fluctuations in entropy are enormously small, and I think, well, there is a chance that in our lifetimes it will not be testable. So I was thinking about non-equilibrium thermodynamics because we are entering the realm of non-equilibrium thermodynamics. People say, well, temperature and all this kind of stuff can be defined only in thermal equilibrium. Well, I've gone through the whole literature of non-equilibrium thermodynamics, and the pinnacle, the stepping stone for this, what are called classical irreversible thermodynamics, which is pioneered by the work of Lars Onsager, who won the Nobel Prize in Chemistry. The pinnacle of this theory is that you can still talk about temperature and entropy out of thermal equilibrium. And that is called the local hypothesis of thermal equilibrium. You say, okay, it is not possible to talk about globally about temperature and entropy as we did in equilibrium thermodynamics, but we can still talk about temperature and entropy if we add a space-time dependence to these functions. So we take these functions as local functions of a space-time, and in that way you can still define temperature and entropy for even out of equilibrium. So again, I said there was a problem with this, and if you equate that kT to mc squared for electron, well, the temperature of electron is ridiculously large. I think it is even more than the temperature of Big Bang. So that is a serious problem. So I saw there is a conservation of entropy in that local thermal equilibrium hypothesis of Onsager's works, and there is a conservation of entropy density. So for that, we know whenever there is a conservation of entropy, you can create a field theory easily. So in this parallel description, single particles possess entropy, and this, for me, I think it resonates better with that another maxim of mine, which is elementary particles are very much like black holes. No, they both possess mass, they both possess a spin, and electric charge. So I think they are formally the same, not numerically, formally. Formally they are the same. So I think if a black hole can possess entropy, then so can a single particle. So another conclusion of that is a field theory for temperature. Well, it is much better because we have lots of problems with the heat conduction and stuff. But I think this work was a spin-off of that pursuit of unification of gravity and electromagnetism. Well, there are many details, and we can talk about them. But let's go to our main theme that we come, and that is historical thought experiments. In these historical thought experiments, well, that was not the point of Schelling or Hegel, but I have a very childish reading of them and say, okay, let's think how the author of a groundbreaking theoretical discovery would have thought and pursued their strands of thought if the situation in which they found themselves was different and to the benefit of solving our current problems. So if you look at in that light, F equals ma, which you write neatly without any constant, everything is neat because it was the first equation that was discovered, not the first equation, well, the first law. Historically, it was the first attempt of talking quantitatively, and that is why it set dimensions. Dimensional analysis was set by this equation. So if, for example, we assume that electric charge was discovered before mass, well, we might propose this equation. Well, this is the simplest one you can propose. Only a constant, and if you want to treat mass and electric charge on completely equal grounds. So let's say what are the implications of this one. So, well, the Lorentz force, we know it, and the geodesic equation, we know it. So the fact that we need this constant is not that, for example, Einstein set the dimensions of metric tensor. No, Levi-Civita connection has already, from the geodesic equation, it must have dimensions of over length. So that must be dimensionally consistent. So if we equate that with the Lorentz force, we get this. And this is a kind of Maxwellian version of equivalence principle. It says acceleration is the same as electromagnetism. So if you compare the equations in the weak field approximation with the Maxwell equations in Lorentz gauge, you can deduce 4 consequences. The first one is that the constant kappa is the same. The perturbation of the Minkowski metric is given in terms of potential, so it is respecting the lesson of general relativity, which was there must be no more potentials. And the energy momentum tensor of the electromagnetic field must be given in terms of the current density. So if you do these identifications, and electric field is easy, it only remains how to treat the magnetic field. And for the magnetic field, you use dipole approximation for the potential, and that is easily circumvented. So the metric, Dr. Rovelli, are you hearing me? Oh, well. Dr. Rovelli. I assume you are not sleeping. You are muted.
I'm following.
What?
Go ahead. I'm listening.
So this is the metric that you get. Well, and if you let the potential to 0, you get the Minkowski metric. So to get Maxwell's equations, you simply define the electric and magnetic field according to the potentials. And to get the Lorentz force, you do the similar approximations. Only the middle one seems new. And this way, you can get a geometrization of electromagnetism. And that brings me of whether the observation of gravitational waves, what is called gravitational waves, in the LIGO experiment was an evidence was it an evidence for gravity waves or it was an evidence for geometrization? I think it was an evidence for geometrization because what was observed were contractions in length. Not you cannot observe waves of gravity per se. So um, all of this work rests on a fundamental assumption that electric charge and mass must be treated completely equally. And and well, I have hesitations about that, and I think if this analogy is perfect, there must exist a similar particle to the Higgs particle, which gives vector bosons electric charge, if this analogy between electric charge and mass is perfect. So there might be some proposal for a new particle, but as you can see here, so that was this. So and the question is now, how do you put geometrized electromagnetism and GR back together? So the reason that I haven't done this is that I still have hesitations whether this analogy between electric charge and mass is perfect. So if that is true, and the simplest choice for constant is this constant, well, we must modify Newton's second law, and people must say, okay, but this might be the case that what we observe as the mass of a particle is in fact the sum of its mass and electric charge. And that is a problem. But I say, well, that is not quite a serious one, because if electric charge and mass are not totally independent quantities, you can just, you must get, for example, the charge of electron by multiplying in its mass with this constant. But that is not the case. That is not true. So mass and electric charge are totally distinct parameters. So that is an answer to that one. This was the first theme. And the second one is problems with quantum mechanics. Well, I consider probabilities, which are not only epistemological but ontological probabilities, as a problem. We don't really know what is the wave function. Well, we can interpret it as a probability, but from the worldview of many people, not just me, that is not just satisfactory. The third problem is that I think we have no satisfactory definition for a spin of particles. Well, we have Pauli-Lewinsky vector, but I think that confuses for momentum with a spin. While I think that a spin and momentum are totally distinct entities. The problem is there is no description of entanglement, and there is universal agreement on the fourth problem. So this brings me to what do we consider in physics as needing explanation? And that again brings me back to epistemology. And a very important point I want to emphasize in epistemology is what Descartes found out. And that was extension, res extensa, is an important foundation for epistemology. Well, Descartes made ontological, also ontological conclusions of that, but I'm not brave enough, as many people, as you, Dr. Rovelli, to go to ontology, because I think, well, I know nobody who has gone to ontology and come back uninjured. So what I want to talk about, I only restrict myself to epistemology. And that is, I think, res extensa. Extension is one of the foundations of the way we think about objects in our mind. So you can simply see that. Just try imagining a mathematical point particle. Well, I cannot, Kant couldn't, and well, there might be people who say, well, I am genius enough who can think of that, but I just do not think evolution works so enormously fast from the time of Kant to now that we can now conceive of any mathematical points in our mind. So this is something very important that I must emphasize. I am not saying you cannot have a theory which says there are mathematical point particles out there. I am not saying nature is not like that. The only thing I am saying is that the way our mind works, the way we think about our theories, is that we always need extension. So, and I have very many examples for that. Well, there is the first example which actually worked ontologically, and this was the old theory of Fermi for weak interaction. Fermi's theory for weak interaction was a point interaction theory. So you just apply extension to that, res extensa, and you get the W bosons. So this is the first one. The second one is string theory. Well, a string theorist wants to understand the world, no doubt about that. So assuming that Feynman diagrams have some sort of reality to them, well, they say these are mathematical points and they are problematic, so we just extend them. Another example. And the third example is Penrose's CCC, conformally cyclic cosmology. Again, what he did was transforming a mathematical point particle, namely that of Big Bang, to using a conformal transformation to a sphere. So what I am saying, again, is not that you cannot have a theory which contains point particles or whatever. The only way I'm saying is that by the power of your subjectivity, and what do I mean by power of subjectivity? I mean the same power which drives us to seek to understand the world better. And that is a very Socratic notion. You know, the whole point of Socrates was that I am a sujet in the world. I want to know the world. And the first thing is to realize that you are a sujet. And you realize that you are a sujet when you understand that you know nothing. And that is the power of subjectivity. There is always some truth, some more truth, some deeper truth to be found. And as long as that power, that drive in mankind exists, people, because that's just the way the mind of our people work, people are driven to, kind of psychologically driven to create theories which conform to this understanding of epistemology. Another example that I have is that people have a very dumb reading of Kant. People say, well, Kant was stupid. He only knew about Euclidean geometry and he based his entire worldview on that. Well, that is a very dumb reading, like you are paid to go to refute Kant. The way that Kant talked about this, and he made huge efforts. He made huge efforts to clarify this point. That again, people make the same mistake of confusing Kant's epistemology with Kant's ontology. Kant never talked about ontology. All he talked about was metaphysics. And metaphysics in Kant's time was understood as synonymous to epistemology. So again, Kant said, it's fine if you have a theory which contains mathematical points. I have no problem with that. I don't know how the world really works. In the real world, which he called the world of Newmans, so in the world of Newmans, there might exist point particles. Anything you can imagine might exist. I am not saying you cannot have a theory. I am not saying if you have such a theory, it would be wrong. The only thing that Kant made huge efforts, in some 20 pages, to clarify this position, that what all that I am talking about is epistemology, and that is the limitations of our knowledge. So, as long as the power of your subjectivity exists, in which you seek truth, that drive to create extended theories exists. So I would not be surprised if someday a string theorist transformed that single one-dimensional string into a tori or a tube. I would not be surprised at all, because that's the way it always should work. There is always, we can dig deeper, and that is the same problem with the singularities of the black holes. Not the event horizon, but r equals to 0. So what r equals to 0 is a mathematical singularity. The only way you can get out of that is to extend it. So this brings me to what do we consider in quantum mechanics as needing explanation. So having in mind that the basis that we think about theories, epistemology, the basis of that is extension. I consider not the problem for me in that light is not how continuity arises from discreteness. What I consider as needing explanation is how discreteness arises from continuity, from extension. And we have some sort of explanation for that. It always boils down to compactness of some space. So there is a principle of finiteness here. Physical world is finite, and we can easily translate it to that finiteness, to compactness of some space. And using compactness, you get packets. There is the old example of strings that if you restrict, if you use a compact geometry in which you are solving the wave equation for a string, you get discrete harmonics of the wave. So in that light, what I consider as needing explanation is how momentum, which is a function of time only in classical mechanics, how is it transformed to a field? Because, this derivation I think is new. You can, if you assume Newton's second law, but momentum as a function of trajectory and time, and using the Broglie hypothesis, you can derive Schrödinger equations from that. So another thing that in that light of epistemology I consider as needing explanation is imaginary unit. And the other one is quantization, as I just said, and entanglement. So this brings me to a new perspective on quantum mechanics. And this is really serious. And I have tried to explain this to people, and nobody really understood what I'm saying. So I can prove instrumentally to you that if you that quantum mechanics is all about E equals h bar omega. Well, that is controversial, but I can show you that how to think in that light. So if you think in that light, you are going to get a guiding equation for Bohmian mechanics, which has an extra additional term. And I think Bohmians are just throwing away the imaginary part. I talked about this before, and that is their definition of wave vector. And if you follow that line of thought, you will arrive at a nonlinear equation. the way I think Bohmian mechanics works is that it only works for uniform probability distributions, uniform amplitudes, and that you can see from here. To get that guiding equation of Bohmian mechanics, you have to put that gradient of r, which is the amplitude of the wave function, or the real part. You must put that equal to 0. And that means Bohmian mechanics works only for uniform probability distributions. And Professor Jung, well, he has a very good paper, serious objections to Bohmian mechanics, and he seems to provide some empirical evidence for that. And I talked about this with him, and he totally agreed that is the way that he wants to emphasize on that. So in this light, Schrödinger equation and guiding equations are not totally independent. So Bohmians say that we hold Schrödinger equation and we add an additional equation. Well, these two equations this new equation that they are adding is not independent from Schrödinger equation. So there is a kind of redundancy in Bohmian mechanics. The whole view of Bohmian mechanics is that we have no operators, we have numbers, and you can see that clearly from their definition of the guiding equation. So how I see this, I see, okay, there is a law of nature which says E equals h bar omega. So not all waves in nature possess frequency. And I will come to that in detail, but briefly, there are two ways that you can brute force all waves in nature to possess frequency. One way is to use operator definition. The other way is to use this definition of Bohmian mechanics. If you use the operator definition, the eigenvalue approach, that is the eigenvalue approach, you will get to orthodox Copenhagen quantum mechanics. But if you do this, you will get, well, first, the guiding equation contains an additional imaginary term and also a nonlinear Schrödinger equation. So there is a duality of approach in current Bohmian mechanics. So let's get more rigorous about my objections to E equals h bar omega. Well, E equals h bar omega essentially boils down to frequency. And the way we understand it is that it is the frequency of de Broglie waves. So there is a kind of wave here. So now let us ask, what is a wave? Well, the best definition you can give is from the wave equation. Wave is a dynamical function that satisfies the wave equation. Even if you take Schrödinger equation as defining a wave, again, there is no frequency in that. The only characteristic of a wave is its speed of propagation. So frequency is not a general enough concept for waves. Not all waves know frequency. But if you want to force all waves to have frequency, to be monochromatic, well, you are led to either Bohmian mechanics or the orthodox quantum mechanics. So there are two reactions to this objection. The first reaction is the conventional approach. It says, okay, if we have a law of nature, E equals h bar omega, which says frequency is fundamental, then so be it. We brute force everything to have frequency. And that has also another problem. That is the problem of basis dependence. Let us consider this from a mathematical perspective. If we want to consider it from that mathematical perspective, we must go to Fourier analysis. So let's talk first about Fourier series. So what is a Fourier series? It is a, not the, it is a basis for our function space of square integrable functions. A basis, not the basis, right? So from that perspective, we are having a fundamental law of nature which is basis dependent. So what I say is that a law of nature cannot depend on our choice of basis. Fourier basis is but one among infinitely many bases that you can find for your space. So orthodox quantum mechanics says, okay, that's fine. We work with that basis, having in mind that we can always express our final results independent of basis. But that just doesn't work. So just consider this E equals h bar omega for a single photon. If that is the way, you must get, by inverse Fourier transform of this equation, you must get the energy of a single photon as a function of time, which is evidently divergent. So this just doesn't work. And I guess that is the foundation of all divergences in quantum mechanics. That is the root. The other approach, which I think the right way, is to find the basis independent interpretation. So how is there any way that we can think of E equals h bar omega, which is not basis dependent? So, well, yes, there is. There is only one instance of frequency in all of physics that is basis independent. Well, there are only two. Either it is frequency of a wave or it is frequency of rotation. So what I am proposing is to reinterpret that omega as a frequency of a spin rotation. I have to add something here, which is, if you want to explain EPR experiments, if you want to explain them, this might not be the right interpretation. We might need to change that. We must look at it, but I think it is at least has the privilege of not being basis dependent. So if you do that, if you follow that line of thought, you can find this equation, which is telling you that wave function is a kind of potential for this field of angles. Well, it is not a potential in the exact familiar sense, which we know from electromagnetism and field theories. It is a kind of double potential. So there is this function, and again, it is in turn expressed in terms of wave function. So, and there is an easy way to see this. I say, okay, wave function. Let us take wave function seriously. Okay. What is the physical dimensions of the wave function? Well, it has no dimensions. It is a pure number. That is why you can interpret it as a probability. Because probabilities are just numbers. Well, isn't there any other physical quantity in physics which is dynamical, well-defined, and yet without dimensions? Well, the only dynamical entity in the whole of physics that is that way without dimensions is angle, which is measured in degrees or radians. Well, both of them are without dimensions, without physical dimensions. That is why frequency, the dimension of frequency, which is hertz, is per second. That just from the definition, it means that angles are without dimensions. So by a stretch of principle of identity of indiscernibles, I am telling that a better, it has many virtues, it is basis independent, and it is not probabilistic, at least. So the better interpretation of the wave function is that it is not a probability, but it is related to angles. So what is the exact interpretation of angles? That must be reconciled with trying to explaining correlations which are even possible in a space like distances. So this way, non-locality kind of arises from locality. Well, we have I propose that there is ontologically distinct space called the space of angles. This new space has its own notion of locality, completely independent from space-time. So if this angle, it might be the angle of precession from spin axis. I need to find that the exact interpretation. But it is right now kind of explaining that how non-locality arises from locality. Two particles which have a sufficiently close angle, and that is, I have provided an exact measure for how sufficiently, what is the measure for that sufficiently. If two particles are sufficiently close to one another, they can be correlated, irrespective of their space-time separation. So what is this omega? This is, I think, the maximum frequency in the world. It might be the Planck frequency of orders 10 to the 43 hertz. And it also brings gravity somehow. And also it is the ultraviolet cutoff. So both of them are considered. And this way you can give a dynamical definition for a spin of particles. Well, that was the theme about quantum mechanics. So I think well, yeah, that is the additional part. But I think if there are any points, we can go to a discussion about them, and or if you prefer, we can continue it. There is, as I said in the beginning, a kind of bonus part. Which it talks about dimensional analysis, taking dimensional analysis more seriously than it is considered now. And the other one is that how can talking about non-local field theories classically. So that is your choice. I don't know, what do you prefer? We can go to the discussion, or we can continue that if you have time. So, what is your proposal?
Jamali, I have to go now. It was interesting to listen to you, but now I have to leave. So just whatever you want. So I just thank you.
Thank you very much for honoring me. I hope I could have lived
to listening to all your ideas.
Thank you very much.
And I hope one day we can meet in person. I'll always be
sure.
And see there. Bye. Bye.
Thank you. Bye. So, other participants. Well, you can talk now. Other participants, please talk. What do we do? Can go to discussion or not?
I would prefer if you'd continue.
Well, thank you. Other people, please, everybody, tell me, are you all in favor of continuing, or we shall go to a discussion? Well, you can just give it a thumbs up.
I think we can go on.
Very good. Okay. Let's go on. Well, the bonus part that I wanted to talk about is about dimensional analysis. I think dimensional analysis is more serious than what is usually thought about. The way I see dimensional analysis is not as a check tool, what is this background? Okay, let's continue. The way I see dimensional analysis is just more than a checking tool for that your equations are consistent. The way I see it is that it is a new tool for arriving at new equations. Two most important equations that I want to talk about are E equals TC5 over G and E equals LC4 over G. These equations I consider as giving very good clues to dark matter or dark energy. From a simple-minded approach, it means if you have enough time, you can create energy well, or the other way around. If you have enough energy, you can create time. If you have enough energy, you can create a space. And this way, it means enough energy can create a space and in turn expand space. So I think I take this very seriously, and well, we can talk about that in detail. That how it works. For example, you can consider a historical thought experiment that somebody, somebody before Einstein and after Maxwell, how he could arrive at E equals mc squared simply by dimensional analysis. And if somebody did, well, we should take him seriously. We should not reject him. So this is from dimensional analysis. And again, if you play with field theories, you can again add this to the source term, and that lambda is the cosmological constant, and you can get a field equation for force, fluctuations in all forces of nature. That is a minor equation. That was one thing. And the next theme is different types of non-locality and infinity. We know using this gravitational potential, you can explain the precession of perihelion of Mercury. Exactly. There is no need for invoke of curvature of space-time. Well, Newtonian gravity has some other problems, but for that it will suffice. So people have tried to create non-local classical field theories, but I think they are not treading on a safe ground. The surest and the safest way I see for making progress in this direction is to use this equation, because it just works perfectly for precession of Mercury's perihelion. So the way we want to do this is just to find a field theory that arises from this kind of potential. And as you all know, you just need to take the divergence. And if you take the divergence of this field, you see that there is an additional term to the Gauss law for gravity. And that additional term depends on the whole energy of spacetime. Everything that there is on a spacetime, this equation sees. There is an integral over the whole spacetime. Yes. So, from this point of view, our classical field theories, which includes Newtonian gravity and general relativity, they are already at infinity. If you let R to infinity, you get Newtonian mechanics, Newtonian gravity, and from that you can get to Einstein equations. That is the way that Einstein himself did that. So our classical field theories are already at infinity, in a special kind of infinity. So even theories like GR, which gets so close to the source, that additional term for Mercurius perihelion gets significant only in very small distances. And Mercury is the closest planet to Sun. So that classical field theories are still, in a sense, infinitely far away from the source. We have another kind of infinity, which is the infinity of asymptotical flatness, but that is different. That is saying that if you go infinitely far away from sources and everything and all matter, you get Minkowski space. This is telling you if you go infinitely far away, you get Einstein equations. So this is non-local, scale dependent. It depends on how far are you from the source. Depending on your distance to the source, the field equations change. So it's a kind of fractal point of view. And it spoils general covariance because it is explicitly including coordinates. So if you look at the attempts of non-local gravity, their Newtonian limit has just no G2, and there are arbitrary kernels. So there is a lot of arbitrariness to the current attempts of non-local gravity. While I think a good non-local gravity must contain at least G squared and no arbitrariness, in such a way that when you find those new field equations, which in approximation would be Einstein field equations, when you solve those equations, you must get this potential. So I think that is the right way to look at non-local gravity. Well, yes, that bonus part is also finished. So if you like, we can go to discussion about them. So please tell me again, what do you want to do? If there are any questions or any objections or anything, I would be glad to hear.
Can you hear me?
Yes.
Yeah. You said that in Bohmian quantum mechanics we don't have operators and stuff.
Yes.
But the point is that we've got some formalism in classical mechanics. It's known as Koopman-von Neumann formalism. They formulate classical mechanics by operators and Hilbert space. Have you noticed them? This formulation, I mean.
Well, yes. So continue your point.
I wanted to object that we can have operator in Bohmian quantum mechanics.
I am not saying that you cannot have. I'm saying there is a duality of approach. But just look at the way that you arrive at the guiding equation, right? The guiding equation, there is no operators in that.
But we can turn it into operators formulation and stuff.
Okay, if you turn it into operators, then there will be no path.
No, because when you see Koopman and von Neumann formulation for classical mechanics, they can define trajectories for particles. It's not the point. You cannot actually define trajectory for particles because they do not commute, as far as I remember. But in classical mechanics, when you see Koopman and von Neumann formulation, the commutation is zero. They commute. Then you can define trajectory for particle. So I mean, you can define operators, Hilbert space, and stuff in Bohmian quantum mechanics and have trajectories.
Well, tell me how you can have trajectories using an eigenvalue problem.
I think we should go into the details of Koopman and von Neumann, and we cannot actually have this detail in this seminar. Yeah,
Okay, so
but it's possible. I mean,
well, I disagree with you, but okay, we can go to that later.
okay.
Um, any other objection, question?
Let me ask another question because
Thank you.
yes, why should you get the temperature at the basic unit?
Well, you can get entropy as a basic unit.
Um,
Okay, you want to measure temperature, right? How do you
okay,
measure it?
by kinetic energy or something like that.
Well, that is just my point. The current definition, which is saying that temperature is the average kinetic energy.
Yeah.
That is, I'm just saying, look at that equation and look at how T is written. T is average kinetic energy over Boltzmann constant, right? And look at the dimensions. What is the dimensions of Boltzmann constant?
Mm, I don't remember.
Well, it is joule per Kelvin. So you want to define temperature, and you are using dimensions of temperature in defining temperature. It is just a circular definition. As simple as that. I just cannot see why people resist on this. It's very simple. I cannot see why people resist on this.
Mm, okay, thank you.
You're welcome. Thank you for your question. Well, why this background is here? So any other question? Well, any other question or objection, I would be glad to hear. If you want to talk Persian, okay, just go on, whatever you want. So, no questions, no objections, no discussions, no, I don't know, idea. If there is none, we can, I think, end the session. Okay, I think there is none.